The last section of chapter 3 involves a few of the theorems that we are going to be using throughout the first semester and the second semester, and they will creep up on you more toward the second semester. First, the mean value theorem, known as MVT, mean value theorem. The mean value theorem basically tells us that given given an interval, so say from A to B, all right. If we were to find the secant line from A to B, and the secant line from A to B can be described by f of B minus f of A over B minus A. That would be the secant line, the slope of the secant line from A to B. The mean value theorem says that there will be some point between A and B such that the slope at that point will be the same as the slope of the secant line. This is only true if your function is continuous and differentiable on A to B. All right? So again, here's what the mean value theorem tells us. If our function is continuous from A to B and it is differentiable on A to B, then the secant line, the slope of the secant line, the value of the slope of the secant line is the same as the value of the derivative of some point between A and B. All right, and that's why they're equal. And again, since the slope are the same, the lines are parallel because parallel lines have the same slope. So let's go ahead and take a look at an example. Let's go ahead and take a look at an example and see if this satisfies the mean value theorem hypothesis. So we're given an interval from 0 to 3. So I'm just going to do a sketch here from 0 to 3, 0 to 3. And we want to know whether or not the hypothesis is satisfied. So the first thing we have to check is the function continuous from 0 to 3? And the answer is yes, it is, because this is a parabola, which looks like this. Okay. And is the function differentiable from 0 to 3? And if you look at the function, it is differentiable from 0 to 3. So yes, the hypothesis is satisfied. Hypothesis for mean value theorem is satisfied because f is continuous on 0 to 3 and differentiable on 0 to 3. Differentiable means it has derivative. Are the conclusion satisfied? So the conclusion is this: there will be some number, some c, there will be some c between 0 and 3. There will be some number between, there will be one number, or it could be, there won't be two c's, but there will be one c between 0 and 3 such that the derivative at that point is equal to the value of the slope of the secant line. And remember, the secant line is this. All right. So first, we go ahead and we find out what is this value. Well, f at 3 is going to be f at 3. You plug that in, you get 9. 9 minus 6 is 3. So f at 3 is 3. And if you plug 0 in, you get 0. All right. Which gives us 1. So the mean value theorem tells us that there is some number between 0 and 3 such that the slope at that number equals to 1. Now, if we want to, we can find out what that number is. So what I do is I will go ahead and take the derivative of this. So I go f prime equals to 2x minus 2. And I want the derivative to equal to 1. So take 1 and plug it into the the derivative function. And then by solving for x, I will be able to figure out the x value that spits out a derivative of 1. And if you solve for x, you're going to see that x equals to 3 over 2, which is 1.5. Or c equals to 1.5, right? So the point 1.5 is the point that has the same slope as the slope of the secant line. All right. So yes, the mean value theorem is satisfied for that one. Another theorem that we're going to encounter is what's called the Rolle's theorem. Rolle's theorem is very similar to the mean value theorem. The only difference is Rolle's theorem tells us that our function, our interval from a to b, must have the same y value. In other words, the point that we start, and I don't care how the function behaves, but it has to return to the same position. So the output at the beginning of the interval has to be the same as the output at the ending of the interval. So Rolle's theorem says that if you start, if f at a equals to f at b, then there will be some point between a and b such that the slope equals to 0. All right. So see, if f is continuous and fa, so it doesn't matter what it is, but if fa equals to fb, then there will be some point in here such that the derivative at that point equals to 0. And that point might be this point because derivative at that point equals to 0. It might also be this point. But Rolle's theorem guarantees us that there has to be at least one point, one c, such that the derivative is equal to 0. Looking at this example from 1 to 5. So if we are given the interval from 1 to 5, here's 1 and here's 5. F at 1 equals to, if we plug 1 in, I get 1 minus 6, which is -5, -5 plus 1 minus 6, which is -5, -5 plus 1 is -4. And if I plug f at 5 in, guess what? I also get -4. So the function, the function is going to behave something like this. The function is going to open up. The function will start at -4 and will return to -4. The function goes up. So the function goes something like this. All right. So what can Rolle's theorem tells us about this function? Rolle's theorem says that between 1 and 5, there is a point between 1 and 5 such that the derivative at that point equals to 0, and it's somewhere here, right? So if we want to know where that exact point is, we could go, we know that there's some c such that derivative equals to 0. To find where that c is, we first take the derivative of our function, and then we plug 0 in. So I plug 0 in and solve for x. You're going to see that x equals to 3. So at 3, the derivative at 3 equals to 0. So c equals to 3. Okay, that's the point we're looking for if you want to. All right. Remember, you can only quote Rolle's theorem if you know the function is continuous and differentiable on the specific interval. Taking a look at this function, notice that this function is an absolute value function. It looks like this. All right. And by just analyzing the function, I can already tell you that the function is continuous but not differentiable from -6 to 4. So Rolle's theorem cannot tell us anything about this function. All right, so you can go, Rolle's theorem doesn't apply because the function is not differentiable at every point from -6 to 4. This is the point where it kind of failed. All right. Increasing and decreasing function, so this is just kind of like a review out there for you. If your derivative is positive, then clearly your graph is increasing. And there's two types of increasing concaving up, increasing concaving down. Increasing concaving down, increasing concaving up. If your derivative is negative, then clearly your graph has to be decreasing concaving up, or it could also be decreasing concaving down. All right, so that's that. Now the constant function, I'm just going to kind of read it over for you because it's pretty simple. It says that if you... That was a long bell, sorry about that. It says that if you have a constant function, if your function is constant, then the derivative of that constant function is 0. Or in other words, if f is continuous and differentiable, and the derivative of f is 0 everywhere, then f has to be a constant function. That's pretty much what the constant function theorem is telling us. Now the last theorem, which I did not write it down, it's called the intermediate value theorem. Intermediate value theorem. The intermediate value theorem says this. Let f be a continuous function on a closed interval AB, then for any k is a number, so for any number between FA and FB, all right, so these are the y on the y-axis, there exists a C, there exists some number in AB such that f, the function value at that number, will equal to k. So let me show you a drawing of what I mean. And this is the best drawing to demonstrate the intermediate value theorem. So the intermediate value theorem says, given a function between A and B, between A and B, pick any, so this is f, this is your f of A, all right, and this is like f of B, all right. Pick any k between f of A and f of B, there will be a C between A and B such that k is equal to f of C. All right, and that's the intermediate value theorem. And that's what it tells us regarding continuous functions. I will give you some exercise on the mean value theorem and the intermediate value theorem, and then we will go over it in class on Monday.